Okay, how do we find out what those equilibrium constants are? What are the values of them? Well, the most direct way is to let a chemical equilibrium. I make up some words. I almost made up a word, density. Is that the study of dance? I don't know. Let an equilibrium establish itself. Measure the concentrations of the reactants and the products at equilibrium. Plug those numbers into the expression, right? So here we've got concentrations of all of the species at equilibrium, and they're asking us to calculate Kc. We have to write the equilibrium constant expression, the equation. Because it's very quick to pull that out of the chemical equation, that's never going to be given to you. You need to remember that pattern of how you write the equilibrium constant expression. And now is where there's going to be some work to show. And so a problem like this, you should always write the expression down first. Don't just put numbers in, okay? So this is going to be the concentration of high squared divided by the concentration of H2 times I2. Showing your work actually saves you time in the long run. If you're doing a problem and you don't care if you get the answer right, well, why are you even doing the problem, right? If you're taking an exam or a graded homework assignment or something, you should write some stuff down, okay? So you write this down so that if you end up with the wrong answer, how do you know it's the wrong answer? Well, Mastering Chemistry tells you, or it's not one of the choices, multiple choice choices. Almost always that means that you are wrong, not the exam. But just a word of warning, sometimes there are mistakes on exams and the correct answer isn't in there. What do you do then? You ask the instructor, okay? The hint, nothing like it ever happened yesterday. Okay, so now we can take these concentrations. H2 is 0.1, but 1,1, but that's not what's on top. This guy's on top. So I've got 0.78, and that one's squared, divided by 0.11 and 0.11. There are many places you can make a mistake, even in a straightforward problem like this one. You could get the exponent wrong. You could write the formulas here in the wrong places. When you plug these numbers in, you could get them switched. I mean, there's just all kinds of things that can go wrong. So if we write down just the basics of what we're doing, we can go back and check. If we make a mistake, we can go back and find out what happened. Okay, so this is the learning chemistry part that we get to. Now we have to communicate this to our calculators. And what I've come to realize is that a lot of students who are very, very good in math class, they can rearrange stuff all day long, awesome. But you give them something like this with numbers and they mess it up, okay? So I'm going to assume that there are some of you that are going to make what is an extremely common mistake. Things like this happen in Chem 1A. So hopefully you got it straightened out there, but if you didn't, I'm going to show you 3 ways to enter this problem into your calculator. So the first way is how I would do it. So this is... you grew up with a really basic calculator that didn't have things like parentheses. And so I would do 0.78 and then that x squared button. And I would divide by 0.11 and divide by 0.11. Students don't like this because they say, but those are multiplied. Well, yeah, they are. But if I have A divided by B times C, that is not the same as A divided by B times C. A divided by B times C, if I just put a times here instead, I'm going to get the wrong answer. So if that makes sense to you, great. If not, forget it instantly just right now. What students tend to prefer is, let's use parentheses down there and multiplication. So this squared divided by, open the parentheses, I'll write this one out, 0.78, press the x squared button, divided by, parentheses, 0.11 times 0.11, close the parentheses. These will give you the same answer. The last option, I think, is really the most straightforward. TI-36X Pro does this. A lot of other calculators also have this button. There is a little button that has a square over a square. When you press that button, now the display is showing you a fraction, and you can type in 0.78 x squared and 0.11 times 0.11, and your calculator understands what you're doing. So choose a method, and let's make sure we can all get the right answer. Your calculator showing you that, 50.28, some stuff. We're going to consider sig figs in this class. We're not going to completely ignore them, but we're also not going to get crazy about them like we did in 1A, right? Phew. When I write this number down, it's good to think about, well, how many sig figs should this have? Well, 2, 2, 2, this one should have 2. As I'm writing that down, I might want to just underline the second sig fig and then recognize that, oh, I didn't need all of those guys. Oops. How many should you write down? Well, I think you should write down a minimum of 2. If you write down 2 extra digits, drop everything else, even if you don't round here correctly, you still won't end up with rounding errors in your final answer. So in lab, when we're entering results into Mastering Chemistry, it is going to require that you enter at least the correct number. I strongly encourage you to type in 2 more digits. The numbers that you enter there with however many digits you put in, those are the numbers the computer is going to use for the future calculations. So if you round everything on the computer and then you use unrounded values like you should to calculate other things, the computer's going to tell you you're wrong because it is going on what you gave it. Okay? So how should we report that? 50. Well, 50 is just a little too ambiguous, so we could call that 50 decimal point or 5.0 times 10 to the 1. That was not meant to be an asterisk. Would you get marked wrong on an exam if you didn't put the decimal point there? No. We don't care that much about sig figs here. Any questions? Okay, so here's a table with a whole bunch of numbers in it, right? Tables are a great way of organizing numbers so that we can see patterns. If this was written out in sentences, I wouldn't be able to make any sense of it. So tables are really useful, but you can't just look at it and say, oh, I know what that's doing. Sometimes you can do that with a graph, but a table, you have to think about this a little bit more. So what do we have here? Here's this equilibrium that we were looking at before, making high. So here we have the initial concentrations for all three of the species and the equilibrium concentrations. And here we have the equilibrium constant. There's the expression, and here they've plugged all the numbers in and calculated it for us. First row, we're starting with only reactants. We end up with an equilibrium constant of 50. Second row, we're starting only with the product. This reaction goes in both directions. So if you start with all product, the product is going to decompose and reform the reactants until the rates of the forward and reverse reactions become equal. So you start with that, you end up with this. How do you know that you end up with that? You would have to measure everything. Plug those in, we get 50. Start with equal amounts of everything. End up with this, still 50. Twice as much of the first one compared to the second one, still 50. Twice as much of the second one compared to the first one, still 50. It's an equilibrium constant. At any given temperature, it will be the same no matter how much you started with. Any questions? Pardon me?
At any temperature or concentration?
At equilibrium. I don't think I understood what you were saying.
So the temperature is constant.
Yes.
For any physical.
Yeah.
Just
If the temperature was changing, then the equilibrium constant would be different. You'd end up with different numbers. Because the temperature, as we'll learn, can affect the position of the equilibrium. But as long as the temperature is the same, you'll always get the same equilibrium constant. Okay. Well, measuring all of the concentrations of all the reactants and products is very tedious and sometimes almost impossible. We can also calculate Kc if we know the initial concentrations and the equilibrium concentration of one thing. Initial concentrations are easy because we decide that when we put stuff in, right? So the experiment we did last week, we had thiosulfate and we had iodide, and what are the initial concentrations? Well, you've got the volume and the molarity of the stock solution. You've got the total volume of the reaction. You can just calculate it using the dilution equation, right? So here, we're going to start with 1 mole of A, or 1 mole per liter of A, and none of B. Then the reaction is going to occur and establish an equilibrium. And at equilibrium, the concentration of A was measured, and it was 0.75. We can, from this information, figure out what the concentration of the other things are using stoichiometry. So if A went from 1 molar to 0.75 molar, how did it change? Negative 0.25, right? So the change here was negative 0.25. The initial concentration plus the change equals the equilibrium concentration. 1 plus negative 0.25 equals 0.75. Everybody okay with that? So looking at the stoichiometry, and not these specific numbers, but if 1 mole of A reacts, how many moles of B are produced? 2, right? So if 0.25 moles of this reacts, how much of this is produced? 0.5, 2 times that, right? So this was the change. So the change for the other one is not negative, it's positive. That's going to be plus 2 times the 0.25. This 2 is from the coefficient. So what's our equilibrium concentration? 0.5. These numbers are most likely not going to add up to equal the number of moles per liter that we started with. So don't even try to make sense out of that. So any questions about how I did that? Now that we have equilibrium concentrations, we can calculate the equilibrium constant. So the expression for this would be the concentration of B squared divided by the concentration of A. So I've got those numbers. So B was 0.50. It's going to be squared divided by 0.75. 0.3333 forever. So let's call that 0.33. Any questions? It's really important to understand the first simple example. And I fully expect that some people will not understand the first simple example. Yes, it's simple, but it's different than what you've seen before. And even some of the things that you've seen a lot, we forget stuff, right? Our mind goes blank. So always, if you don't understand, I want you to ask, okay? Everybody okay with what happened here? Let's do something a little more complicated. So here we have a reaction between carbon monoxide and hydrogen. We're given initial concentrations of the reactants, and we're given a concentration of the product at equilibrium. Now, if we had a problem like this in Chem 1A, we would be doing a limiting reactant problem, right? Because in Chem 1A, we assumed that all reactions went to completion. Well, now we know better, they don't. We could still calculate the maximum amount of this that could be produced from that, but it's not going to be produced, and that's not what we're asking here. So what we're going to do is we're going to make a table just like the one in the previous example. And I find it really convenient to use the chemical equation as the header row. And it might help to put a double line here. Oh, things are getting squiggly. And then the rows were initial, change, equilibrium. Well, we don't want to write out those long words. I, C, E. Remember the song Ice, Ice, Baby? This is an ice table. We're going to be using ice tables a lot in Chem 1B, so here's your introduction. Ice table, I'd like you to meet my students. Students, that's an ice table. Initial, change, equilibrium. So we're going to put the information we're given into the table. In the previous example, it was put in there for us, and we just had to figure things out. So carbon monoxide initial concentration. So for the initial concentration, I'm going to put in 0.27. The initial concentration for hydrogen is 0.49. What's the initial concentration for CH3OH? 0. They don't tell us. It is safe to assume that if they don't tell you the concentration of a product, that they didn't put any other product in there, because that's not what we normally do, right? We don't usually put both of the products and some of the, both of the reactants and some of the product in there. We just start with the reactants and we let the product form. So we're not told this, but that concentration would be 0. We're given an equilibrium concentration for one of these, the CH3OH. So we're going to put that in, 0.11. And what the table is doing here is basically I plus C equals E. The initial plus the change gives us the equilibrium concentration. We have enough information to fill in all the blanks. You're going to have to start with the one where you're given the equilibrium concentration. This started at 0 and it ended at 0.11. What was the change? Must be positive 0.11, right? So this increased 0.11. That's our change. Well, how did CO change? It decreased, right, by the same amount. So we could do the math there and we come up with 0.16. How did H2 change? 2 times this. The coefficient here is 1. The coefficient here is 2. You need twice as many of these to make that. So this is minus 2 times 0.11. So that's 0.22, 0.27, I think. Check my math on that. Any questions? You're going to need to practice this a few times before it sticks in your brain, right? Now we can find the equilibrium constant. We have to write the expression. It's kind of why we practiced so much. So the equilibrium constant, and they're not telling us Kc or Kp, but what are they giving us? It's all concentrations. So Kc. So I'm going to write the expression. This is going to be the concentration of CH3OH divided by the concentration of CO times the concentration of H2 squared. Then I'm going to put my numbers in, being careful to line them up correctly. So I've got 0.11 on top. I have 0.16 and 0.27 squared. Here again, we have something in the denominator that's multiplied. This is going to happen a lot. So get your calculator out. As I'm going to write down what the calculator says, I think about sig figs. Everything here is 2, so my answer will most likely have 2, and so I'm going to write down the next 2 digits. Or sometimes like this one, it would be 0.7, and so then the zeros should get rounded up to a 1, and I don't feel like doing that, so then I'll just write another digit. At least 2. If you're one of those people that wants to write all of them down, bless your heart, but go ahead. It's not going to hurt anything. So the answer for this should be 7.4. Any questions? I have a question. Why did I say the answer should be 7.4? And I wrote 9.4. That's what my husband would call a brain fart. It's 9.4. There's no 7 in there. I don't know where that came from. Maybe. I don't know. But, so feel free to catch me on stuff like that. Sometimes I catch myself, other times not. And then the YouTube people are like, what? And they get all confused. So you're helping society at large if you call me on my mistakes. Okay, let's do another one. Got another chemical reaction. We've got at least one initial concentration given, and we have an equilibrium concentration. Find the equilibrium constant. So I'm going to give you a minute, and I want you to draw up your own nice table and at least fill in all the stuff that's given. So if you're not done, just keep working on it. I'm just going to make my table. Made my table. I'm going to put in the initial concentrations. They didn't tell me what the product concentrations are. What do I write in there? 0. And then they give me an equilibrium concentration for H2. So I'm going to write that in here. 0.012. Everybody with me so far? Okay. Next thing is we need to identify what the change is. So we're going to look at this column. 0 plus what equals 0.012? 0.012. So this went up by 0.012. Okay, great. This equation is a little more complicated because the coefficient here is not 1. It's a 3. And then we've got a 2 over here and a 1 over there. There are different ways that you can approach this. I like to choose the path of least thinking, because the more I think, the more I can make mistakes, right? So this went from 0, it changed by 0.012, but there were 3 of those, right? So that is equal to 3 times sort of the baseline change for everything, right? So x then is going to be equal to what? 0.012 divided by 3, so 0.004. You don't have to do this part, but I think it just makes it a lot easier. If this is a 1 and you do this part, no harm. You're dividing it by 1, you'll find out, oh, well, x is the same, right? Now that I know what the base is, when I go over here and I ask, how does this one change? Well, it has a coefficient of 1, so it changes by 1 of these, right? So this is 1x, so this is plus 1 times 0.004, so 0.004. How much did the CH4 change? By 2x, right? So this decreased by 2 times that value. This one increased by 3 times it. This one increased by 1. This one decreased by 2. Okay? Yeah, I don't trust my brain on that one. This is one where it'd be much easier to mix these up, right, and end up with the wrong equilibrium concentrations. Any questions about it so far? So now we're going to write the expression. Kc is equal to, we got our products, oops, C2H2 and H2 cubed. And in the denominator we have the reactants CH4 squared. So I'll plug my numbers in, 0.012 cubed divided by 0.079 squared. Most calculators have an x squared button because that gets used a lot. A lot of calculators, I'm not sure of any that have an x cubed button. The TI-36X Pro has an x to the box button. And the way you use that is you type in, like here for the cube, I'm going to type in 0.012, I'm going to press the x to the box button, and then I'm going to tell it what the exponent needs to be. Or you can just multiply 0.012 times 0.012 times 0.012. That works also. So my calculator is showing me 1, 2, 3, 4, 5. Did you get that? I hope I'm not the only one like this, but when I see this many zeros, they start to swim around a little bit. And if I try to count them just moving with my eyes, it just, sometimes it works and sometimes it doesn't. So I have to get my finger or my Apple Pencil out and go 1, 2, 3, 4, 5, which makes me feel so stupid. Well, I'm in first grade, I can count to 5. So kind of my rule of thumb is if there's more than 3 zeros, I think scientific notation is better. For some reason, I can see 3 or 2 or 1 zeros and not have to count them. But past 3, it gets a bit iffy. And I know I've helped some of you with various problems, and the answer was wrong because between what was on your paper and what you typed into the computer, you added an extra 0 or you lost a 0, right? It happens all the time. So we should write this in scientific notation. Your calculator can do this for you, but I also want to review how you do this without the calculator, because we learned this in Chem 1A, but we forgot some of the stuff that we learned in Chem 1A, right? in scientific notation, the decimal point goes after the first non-zero digit. So that's going to be right here, the 1. So it's going to be 1.108 times 10 to the something. The exponent is how many places we need to move the decimal. 1, 2, 3, 4, 5, 6. Most people don't have too much trouble with that. Is it a positive 6 or negative 6? It's a negative 6. How do we remember that? This is how I remember it. How do I feel about little teeny tiny paychecks? Negative. I don't feel good about that. How do I feel about big paychecks? Positive, right? This is a little number. That would be a horrible paycheck, right? I would feel extremely negative about that. Less than a penny? You got to be kidding me. So that tells me, in my little weird analogy brain, that that needs to be a negative. Okay? How do you do that on your calculator? So if you have the TI-36X Pro, you did the calculation, you've got the purple number there, press the mode button at the top. And it's going to show you a whole bunch of stuff. At the top it's got DEG, RAD, GRAD, that's changing different units for angles. And there's a flashing cursor. I want to drop the cursor down to the second line. It's currently on norm, most likely. And I'm going to move it over to psi. That's scientific notation. The next one is engineering notation. Don't go there. Unless you're an engineer in engineering class, then fine, but don't do that here. And I'm going to press equals to select that, and then I'm going to quit to get out of there. And when I first started using this calculator, I was like, well, that's lame. Where's my number? I have to do the whole thing again. No, you don't. Just press enter. And it comes back. And now, what it's showing me, I'll just stick this over on the other side where I have some room. Now it's showing me 1.107514821 times 10 to the minus 6. I mean, it's actually showing me E minus 6, but we understand what that means. How did it go from 1108 to 11075 and all those extra numbers? These are the extra digits. It didn't show them here because there wasn't enough space in the display. If your number is so small that all of these are zeros, it will automatically show it you in scientific notation. But there are times when you get a number like this and you might only have one digit at the end and you're like, but I need 2 sig figs. Don't assume that the next one's 0. Put it into scientific notation and then it'll show you all of them. Does that change our answer? No, it doesn't. It's still 1.1 times 10 to the minus 6. Any questions? So you got some review things there. I won't be going over that again, but if you have trouble with things that you forgot from Chem 1A, please ask me, because I don't want that to mess you up learning the Chem 1B stuff. Yay, you got the correct answer.